Okay, so we talked about generation consumption analyses, and we talked about making different routes to design processes, and then we saw a bunch of research where, again, you can see this theme of we're all trying to make stuff, interesting chemicals, cells, fuels, switches, interesting molecular components. So I'm going to continue this theme of how do we decide what's the best way to make something and whether a process is good or not. And so I'll start with some high-scale ways of analyzing this. So you probably read this in the book. First thing I want to talk about is atom economy. So what I want to look at is, let's say we had two processes. How do we know which process is better? And a lot of times it's, well, which one's more expensive to make, but that can take a lot of calculations. We find our calculations on that over the semester. But if we want some really quick estimates, atom economy is a really easy way to do this. This was developed in the 1990s by Roger Sheldon and Barry Trust. So this was developed after the other textbook that they're using in 90% of the chemical engineering departments. So that's part of why I like using this textbook, because they don't really talk too much about these trade-offs and how to figure out the best ways. Okay, so this is a rapid and simple way method to evaluate the efficiency of a reaction. Here's the formula. Fractional atom economy equals mass, the desired product, divided by the total mass of the reactants. That's equal to nu P. So a nu P would be the stoichiometric coefficient of the product. This is the nu we talked about last week. Now, stoichiometric coefficients are in moles, because we do moles in our chemical reactions. If we want to get the mass, we need to multiply moles by the molecular weight. And on the bottom, the reactants, well, we might have several of those. So nu I, mi would be the moles of a reactant, the mass of a reactant. And then we're going to need to sum those over all reactants I. Stoichiometric coefficients for reactants are going to be negative. We want this to be a positive quantity, so we're going to put a minus sign. M sub I is defined as the molar mass. Got into, at the end of the last week, briefly, the LeBlanc and the Solvay processes for making sodium carbonate. So the LeBlanc net reaction is this: 2 sodium chloride plus H2SO4 plus 2C coal plus CaCO3 reacts and becomes sodium carbonate plus 2HCl plus 2CO3, CO2 plus CaS. The easiest way to do this is to make a table. It's the easiest way to make a table. So what I want to do is the compound, the stoichiometric coefficient, the mass, and the product, the stoichiometric coefficient and the mass. It's the easiest tool to use to make a table. So sodium chloride, the stoichiometric coefficient is, everybody? Minus 2. Minus 2. I know you all said the minus. Molecular mass of sodium chloride. 58.5. What's the easiest way to get that? Periodic table. Yes, that's easy, and on the test you need to do it there. What's even quicker than that? Right, and then the product of that would be minus 117. What's the units of 58.5?
Grams per mole.
Grams per mole, and so the units of this? Grams, because this is going to be mole. Mole. Grams per mole. Grams. Okay, the other compounds, H2SO4, carbon, calcium carbonate, sodium carbonate, stoichiometric coefficients, 1 mole of hydrogen sulfate, 2 moles of coal, and 1 mole of calcium carbonate is going to make me 1 mole of sodium carbonate. The masses, 98, 12, 100, 106. Products then minus 98, minus 24, minus 100, 106. Take these together, sum them, I minus for the reactants. We'll get 339. And what did you guys tell me? Grams. You want to be grams. So it turns out I don't have to do this in grams. I could do molar masses in. We'll talk about this more. This mole is a special mole. This is a gram mole. The gram mole has so many grams in a gram mole. We can do this pounds per pound mole, kilograms per kilogram mole. Read that in the book. It's a little confusing. We'll talk about that more on Wednesday. Okay, anyway, we'll call them grams today, so let's say that's grams. And then the product, so these are the reactants. Product is 106 grams. Just that one right there. So our atom economy, we got 106 grams of sodium carbonate from 339 grams of reactants. So the atom economy is about 0.31. For every gram of reactant, I get a third of a gram. 100 grams of reactant, I get 31 grams of product. Means I've got 60. Assuming mass is balancing here, that means how much waste do I have? The other fraction, right? 1 minus that. So 31% products, 69% byproducts, waste. Let's do another example. Solvay process. Solvay took 2 sodium chloride plus calcium carbonate, reacts to form sodium carbonate plus calcium chloride. Any questions about how to do this? Can we do this? Okay, take a minute and a half and crank out the atom economy for this. You got 1.49. Who agrees? All right, good. Okay, easy. Any questions? Very simple, very quick, but it tells you a lot. I mean, it tells you that the mass is going into the product, so it's a really easy way to get started and compare two processes. What does this measure not tell you? Price. So it might be using all the atoms, but it might be using some really expensive atoms. So the next thing we want to look at is process economy. So we really want to ask how much money is the process capable of making. Okay, so the easiest way of doing this would be the cost of the products minus the cost of the reactants. This still doesn't say everything too, right? What else would we be missing? Well, the byproduct, well, okay, if the byproducts are sellable, we could put that into here. Neil? Cost of energy. We could be putting energy in, or we could be getting energy out. Yeah, what else? The quantity of stuff being used we should have in here. We'll see that in a minute. Right. Dan.
Maybe like there's costs incurred with removing byproducts from the reactor, or like running a reaction that would make it like clean or be able to.
Okay, there's the cost of running that process, cost of taking things out. So ultimately, that's either going to come in the cost as energy, we're going to put energy in, or use some materials to do that. So it's kind of incorporated what we've already talked about a little bit. What about some costs of doing business? Where are we going to make this stuff? What are we going to use to make this stuff? Yeah, Alex.
I suppose like building equipment or building
The equipment, so the capital costs, you got to build this plant first to make stuff. You got to build a reactor. The reactors aren't cheap. You got to build a separator. What other costs of business? Just sell it and keep all the money. Maintenance, yeah. Operators, people to pay. Shipping. One more big one. Cost to store it. Somebody else is going to take a cut of these profits. Depending on what country you're in. Taxes, right? So all of those go together. Okay, but for now, because we're just starting to think about things, let's just look at, will the products be more valuable than the reactants? This number's got to be positive. Well, unless we're making energy also, but if this number's got to be good if we're talking about making a product. So, what do we need to know to be able to figure out the cost of the products? Say this and this stuff to see how much money we make each year. What do we need to know? You need a price. So here's some steps to do this. Step one, we'll start with our reaction, say our solvate process, and the first thing we need to do is convert moles to mass, which we just did this for the atomic economy problem. Second, how much we're going to make depends on how much we put through, right? Are we going to make 106 grams? Well, it's not that much. If you're going to set up a business, build a plant, get investors, you're probably going to make much more than that. So we're going to need to scale up or down to your actual amount of production that you plan to do. And then 3, you need to convert mass to money. So that's where our costs come in. Solvay process, for example here, to produce 1,000 tons of sodium carbonate. So step 1, we're going to do moles to mass. I need, now let's look at the product. I need 1 mole Na2CO3. I want to convert that to mass. You guys already did this. I want to convert moles to mass. You guys just did this for me. So you told me you put the molecular mass over the moles. Na2CO3. Na2CO3. You just did this for me, but I wanted to do it this way again. If you've done this form, you do the vertical lines. Okay, this is a good practice. You probably did it in chemistry. It's a good practice to keep doing so we can keep track of our units. Moles of NaCO2, moles of NaCO2, that should give us grams of Na2CO3. Okay. Okay, you do the same thing for minus 2 moles of NaCl, etc. Right? Okay, step 2. Scale up or down. For this, we're going to require a basis. I used that word a few times last week. I want to formally define this because we're going to use it all the time. Basis is quantity or flow rate that indicates the size of the process. In the back that are right on the bottom of the board. That's okay. All right, so our basis in this case is this 1,000 tons. Gives us the size that we're shooting for. Then we can find our scale factor. It's going to be our basis divided by some relative mass quantity. So in this case, it's 106 grams is a relative mass quantity. Our basis, 1,000 tons, 106 grams, NaCO3, grams of NaCO3. It's going to give us a scale factor of 9.43 tons per gram. For every gram in our model calculation, we need 9.43 tons. So I should have done a second one here. The sodium chloride needed 117 grams of sodium chloride. So if I want to scale that up, I can take this 117 grams of sodium chloride, multiply it by the scale factor, 9.43 tons per gram, and get 1104 tons of sodium chloride. Mass to money. How much will it cost me to get 1,104 tons of sodium chloride? Well, we need the price. Where do you get the price for things like sodium chloride? What? Market. Where do we find market prices for chemicals? There used to be a thing, or there still is, there's a magazine called, and I didn't know the answer to this until I started teaching this class. So there's a magazine called Chemical Market Reporter that publishes prices on a monthly basis, how much is stuff running. So you can just look it up in the Chemical Market Reporter. The problem is these guys, unlike most information today that's just out there, this is fairly guarded. You've got to buy a good subscription to this, and it's expensive enough that it's one of the very few things our library does not get. So you can't get this from our library directly, but you can, the last time they published openly was 2006, so there's a 2006 issue. It's pretty old now, where you can get the 2006 prices of these. And then there's also a search page, ICIS, the Institute for Chemical Information, I forget what it stands for. It's described in the book. Do that legwork and find a price. Let's say we get $95 per ton of NaCl. We can take our minus 1104 tons NaCl per day, multiplied by $95 per ton of NaCl. We get $104,880 quality. Some, what's wrong with that number? Oh, yeah, per day. Good, good, good. Per day. That's a good amount to shell out each day. That's half a house. That's actually probably a whole house in Baltimore. A small house. What else is wrong with that number?
It should be negative.
It's negative, yeah. What else? A little trickier. I think chem class, losing a point on your exam. I'll make that thing right. Sig figs. Do I really have, how many sig figs on that? Why are we saying 2?
It's 99 is high.
Okay, there's 2 sig figs here. How many are in this number? 5. Is this the one that's important? That came from, see, 1104, was that one right? Keep track of your sig figs. I'm sloppy on the board. Murphy is also a little bit sloppy, so Murphy loves to put things like 1,000 tons per day, and how many sig figs there? Yeah, so that would make your answer very low precision. Usually, 1,000 tons per day, you usually do want to say, that, I don't want to say plus or minus 10%. I probably want 2 or 3 sig figs. I would probably go, what would I go with here? I would go with 105,000 with my common sense. But even that might be a little too much. I will try to be rigorous on the exams and put those decimal points in, and you should follow your rules of sig figs.
In the winter